In today's video, we'll learn a new method for finding the volumes of a solid. This method is called cylindrical shells. In this particular picture, say we wanted to find the volume of the solid when it's rotated about the y-axis. Well, things that we would note by looking at it is, well, there's a gap, so we know it can't be discs. We would have to try and use washers. We would have to draw in our slice perpendicular to the y-axis, so it would be a dy. Couple problems that we'd run into, though. Since it's a dy, we'd have to get x by itself, and we'd have to solve a cubic. That would be very difficult. The other issue is our function that is our inside and our outside radius would be the same function. Those two issues can be resolved with our new method called cylindrical shells. What cylindrical shells is, instead of taking a region and rotating the whole region around something and then slicing it and finding the volumes, what cylindrical shells does is it takes rectangles of the individual region and then individually rotates each of the rectangles around your line. So instead of rotating the region and then slicing, or you can think of it as we're slicing up the area into rectangles, kind of like we did with our Riemann sums in the beginning, and then rotating the rectangles around. So this is what we would get when we rotate this region around. What we'll do is we'll draw different rectangles in, and depending where those rectangles are, they will create different size cylindrical shells. What a cylindrical shell is basically a cylinder that has had a cylinder inside of it punched out. So like a cylinder with a hole in the middle. Think of like a piece of piping or something. So what is really taking place is we'll have a single rectangle. Say here's a rectangle that was selected by right-hand endpoints. And that single rectangle will get revolved around. And this is what a cylindrical shell looks like. Basically, you have an outer cylinder that's the outer edge, and you have an inner cylinder that was subtracted off to take away that volume that's in the middle. Well, that's just one of them. Notice, depending where we selected our rectangle, the height of that cylinder is different. So our height is going to be a function, and our radius will also be a variable. That will not be staying constant. So if we have a region, we rotate it around. Again, the general idea is we take a rectangle out of the original region and rotate that single rectangle around. Well, when we rotate all of those rectangles around, as you can see by this bottom picture, we get a bunch of cylindrical shells that are kind of sitting inside of each other, all of different heights. Just like everything else we've done, we'll make those rectangles thinner and thinner, and then that volume become a more smoothed out curve that will look similar to what the actual thing does. We know as those number of rectangles approaches infinity and we keep adding them up, that should end up being an integral. We've seen that several times now. Before we get to the integral, we've got to figure out what's the setup inside our integral. When we had discs, we had pi r squared. When we had washers, we had pi r squared minus pi r squared. Well, let's look at this particular cylindrical shell. We're going to call our inner radius r1. That's the radius that's used to find the volume that we would subtract out. And our outer radius we'll call r2. So really what we're doing is we're going to do the big cylinder minus the small cylinder. Now, because we'll see it in our derivation of the formula, justify to yourself that what I'm going to call r, which is this line here, that is a radius that goes directly in between r1 and r2, Justify to yourself that that's just the average of R1 and R2 because it's right in the middle. And we're going to call delta R the difference between R2 and R1. Delta R is really going to end up being our thickness, just like our other thickness. That'll end up being our dx or dy eventually in our integral. That's the role that that will play. So we said we've got to do our big volume minus our small volume, because that'll cut out the center. Well, the volume of a cylinder is pi r squared. So we'll do pi radius 2 squared times height. And then we'll do pi radius 1 squared times height, and that's each of our individual volumes. Well, each of those have a pi and an h, so we'll apply the pi out front and the h at the end. And r2 squared minus r1 squared factors into r2 plus r1 times r2 minus r1, because that's the difference of two perfect squares. Well, this is where you have to get kind of clever to make things work out. We are going to divide this by 2 to get our average that we had. But if we divide by 2, we have to also multiply by 2. That's why we get 2 pi times r2 plus r1 over 2 times the height times r squared minus r1. Now, a couple things we noted on the previous slide. We said we were going to call r2 plus r1 over 2 just r. And the difference in our r2 and r1, we said was going to be our delta r, which will eventually become our dx or dy. So really what we have here is 2 pi r times h, which is really the circumference times h. The things that we'll have to determine always is the r and the h. The 2 pi is a constant. The r and the h will change depending on where the rectangle is. So here's just that same formula written nicely again. In reality, 2 pi r is the circumference again, h is the height, and our thickness is that delta r. Again, that delta r will end up becoming our dx or our dy in our integral. Just like all the others, we'll make those rectangles as small as possible. We'll add them all up. As the number of those rectangles goes to infinity, that'll eventually become an integral, where this is our radius and this is our height. So your height is some function, and your radius is also a variable. So that integral will be the exact volume of our solid. Now, in reality, what we're finding, if you kind of unravel it, is we have a rectangular prism with thickness delta x. And let's look at an example. We're going to look at 2x squared minus x cubed, that thing we looked at in the beginning. If we remember, our picture kind of looked something like this, where it hit back at the x-axis at 2. Now, there's two main differences with cylindrical shells compared to the others. The first thing is you're not drawing in a slice, you're drawing in a rectangle. When you draw in that rectangle, it needs to be, the long part of the rectangle needs to be parallel to the thing that you're rotating around. So I'm going to draw our rectangle in here with the long side parallel to what we're rotating around. The thickness of that rectangle tells us the dx or the dy. In this case, our thickness of the rectangle is in the x direction, so we'll have dx. Our x's in the region are going from 0 to 2. And remember, we are going to have 2 pi rh. Well, the 2 pi I'm just going to stick out front because that's a constant. We've got to figure out what's our radius and what's our height. Well, the radius is the distance from the rectangle to the line that you are rotating around. So for us, it's this blue line here. That's the distance from the rectangle to the y-axis. Well, notice that's connected to the y-axis, so that's just an x. And because we're in dx, we can just go ahead and put that in as x. So that takes care of our radius. We now need to multiply it by the height. Well, the height is just the height of your rectangle. So the height of our rectangle is this red line right here. Well, that height is just connected to the x-axis. We know that's a y. Well, we can't put y in for the height because we're in terms of dx, so we have to put what y is equal to, which is 2x squared minus x cubed. And that's our setup for the cylindrical shells. Again, we drew a rectangle whose long side is parallel to the line that we're rotating around in this method. The thickness of the rectangle tells you dy or dx, and then you're drawing in the radius from the line you're going around to the rectangle, and your height is just the height of what that rectangle is. And now we can just evaluate this. We'll have 2 pi, 0 to 2. We'll have 2x cubed minus x to the 4th dx. So we'll have 2 pi. Our antiderivative will have x to the 4th, so we'll multiply by 1/4 out front to get 1/2. And we'll have minus 1/5 x to the 5th, evaluated from 0 to 2. We'll have 2 pi, 1/2 times 2 to the 4th, minus 1/5 times 2 to the 5th, minus the whole quantity. When we put in the zeros, that wipes everything out. So we'll have 2 pi, 2 to the 4th is 16 times 1/2 is 8. 2 to the 5th is 32 times a negative 5th is negative 32 fifths. Well, 8 is really 40 fifths. 40 fifths minus 32 fifths is 8 fifths. So we have 2 pi times 8 fifths, which will give us 16 pi over 5. That is the exact volume of our region when it is rotated around the y-axis. And here's another visual of that. We've got our rectangle that we drew in. Our radius there is x. Our height is a y, but we can't put it in as y. We need to know what y is equal to because our thickness was in the x direction. All right, next one will be a region that we've worked with quite a bit. We'll do y equals x and y equals x squared. We've seen that in several problems in our videos. We're going to do it with shells and rotate it around the y-axis. So we need to draw in a rectangle. Now keep in mind, the top of your rectangle in this case and bottom in this case, I say top and bottom in this case because our long side is going to be parallel to the y-axis, so the short sides will be the top and bottom, but your top and bottom should be at the top and bottom of your region. So our rectangle should look something like this. Again, the long side is parallel to the line you're rotating around. Thickness of our rectangle is in the x direction, so our integral will have a dx. Our x values go from 0 to 1. Keep in mind we're looking for 2 pi rh. We'll put the 2 pi out front. Our radius should connect our rectangle to the line we're rotating around. Well, that's connected to the y-axis, so that's just an x. And because we're dx, we can put that right in. Now, our height of our rectangle is going to be a little bit trickier here. It is that blue section. Well, that blue section is not connected to an axis. But if we put the blue and the green together, that is. The blue and the green together is a y value. The y value that is together would be the y equals x. So the blue, let's say we call this y1 and y2 just to make our lives easier. So the blue and the green together is y1. To get what we want, just the blue section, we need to chop off that little green part. Well, that's still connected to the x-axis, so that's a y, but that's y2. That's the y from the y equals x squared. Well, y's we can't put in, so we need to put in our x's. Well, y1 went with x, y2 went with x squared. So really our height is just x minus x squared. It's the y on top minus the y on the bottom, but we can't do y's. We have to do x's because we're dx. And again, that's a bit more challenging than the last one we just saw. Well, our integral is now set up. We'll distribute our x to give us x squared minus x cubed dx from 0 to 1. When we take the antiderivative, we'll get 1/3 x cubed minus 1/4 x to the 4th, evaluated from 0 to 1. We'll have 2 pi. We'll put in our 1. And then our 0, everything will get wiped out. So we'll have 2 pi times 1/3 minus 1/4. A third and a fourth will need a common denominator of 12. So that'll be 4/12 minus 3/12. So this will be 2 pi times 1/12. So that'll be 2 pi over 12, which is really just pi over 6. Now, this particular case, we've seen ones where we did it with washers. So we're actually going to show you in a second how you can do this with washers and you'll get the same answer. Sometimes there'll be ones that you can only do with shells. Sometimes there might be ones you can only do with washers or discs. For example, if you can't get a certain variable by itself, if you're trying to do like one method, try the other method then. The reason that's helpful is if washers and discs uses a dy, the shells in that same scenario will use a dx. So it switches the variable you'd have to get by itself, which can help you out. Here's a picture of what we just had. We had our shell height, which was the y on top minus the y on bottom, which was x minus x squared. And then that rotated around to give us our cylindrical shell. Now we're going to show you that we could have done the same thing with washers and also gotten that pi over 6. We were going around the y-axis. Now remember, when we do washers, we draw on a slice, the thickness of our slice, and again, that slice is perpendicular to what we're rotating around. Thickness of our slice here is in the y direction. Our y values go from 0 to 1. Because we have a gap, it's not all resting against the line we're rotating around. We'll have to do pi r squared minus another pi r squared. Our outer radius is the red there. Well, that's just an x value. That x value, that's represented by the y equals x squared equation. So x would be equal to the square root of y, which is also y to the 1/2. So that was our outer radius. Our inner radius would be this blue part here. That is also connected to the y-axis, so that's just an x. But that x corresponds to our other one. That x was just y. Again, we needed them in terms of y because we had dy. Now notice, dy in this case when we do washers, it was dx when we did shells. That's why knowing both methods is important. If you have a function that you can't get either x or y by itself, do the other one and you'll be able to work with it. So we'll pull the pi out. We're going from 0 to 1. Square root of y squared is just y minus y squared dy. We're ready for our antiderivative. We'll have 1/2 y squared minus 1/3 y cubed, evaluated from 0 to 1. We'll plug in our 1. We'll have 1/2 times 1 squared minus 1/3 times 1 cubed, minus the 0 wipes everything out. So we'll have pi times 1/2 minus 1/3. Common denominator would be 6, so that's 3/6 minus 2/6. Well, what do you know? That's pi times 1/6, which is pi over 6. So notice both methods got us the same thing, meaning both methods will work equally. So again, when it comes to a test or quiz, some of them I might tell you which method to use. Others methods you might have to determine which one you could use. And there might be cases where you could use either, or even in cases where you could use either, there might be one way that's easier than the other way. So you always want to try and look for the easiest way possible. So our next one is telling us we're going to use shells. We're going to take the region y equals square root of x from 0 to 1. And that region under the curve, so between that and the x-axis, and we're going to actually rotate it around the x-axis. So our region's going to look something like this. Now we did this with disks in a previous video. We'll start out, we have to draw in a rectangle. The long way of our rectangle needs to be parallel to what we're rotating around. So we'll draw in something like that. So remember, the rectangle should start and end at the edges of your region. The thickness of our rectangle is in a y direction, so we'll be dy. Our y values go from 0 to 1. And keep in mind, we're doing 2 pi rh. So we'll do the 2 pi out front. Our radius is the length from what we're rotating around to our rectangle. Well, that is connected to the x-axis, so that's just a y. And because we're doing dy, we can just go ahead and put that right in. Now, to find the height of our rectangle, notice that height of our rectangle, it's not connected to an axis. Well, if we put in the red and the height of our rectangle, together, those must equal 1 always, because we've got a vertical line there. Then we want to chop off the red. Well, the red is connected to the y-axis, so it's just an x. So our height is just 1 minus whatever x is. But we can't put x in because it's a dy. So using our equation, we know x is really equal to y squared. So our height is just going to be 1 minus y squared. We have our integral set up. Now we just need to evaluate. We'll have 2 pi from 0 to 1 of y minus y cubed dy. When we take the antiderivative, we'll get 1/2 y squared minus 1/4 y cubed, evaluated from 0 to 1. We'll plug in the 1. And when we plug in the 0, it wipes everything out. So we'll have 2 pi times 1/2 minus 1/4. Well, 1/2 is really 2/4, so 2/4 minus 1/4 is a 1/2. Or sorry, a 1/4. And a 1/4 times 2 is a 1/2. So we'll get pi over 2. Now again, we saw that same problem, rotating square root of x from 0 to 1 around the x-axis and use disks. And we just showed now that you can also use shells to find that. And here's another visual of that. Again, to find the height of that rectangle, this length was 1. We chopped off this length of x, so 1 minus x, but x was really y squared. So the height of our rectangle was 1 minus y squared. One last example for this video. We're going to take x minus x squared, and the region of that bounded with y equals 0, which is the x-axis, and x equals 2. So here's x equals 2. Or sorry, I should say we're going to rotate around x equals 2. Our region is just going to be bounded by y equals 0 and y equals x minus x squared. Well, to find our roots of this, if you pull an x out, you get 1 minus x. So our roots will be at 0 and 1. So we'll look something like this for our region. And we're going to, again, rotate that around x equals 2 using shells. Now, reason we couldn't really do washers here is, although we have a gap, which might tell us washers, our inside and outside functions would be the same thing. So that's why we'd want to use shells here. We'll draw in an example rectangle with the long way parallel to the line we're rotating around. The thickness of that rectangle is in the x direction. And let me just mark these up so you know which is which. That's x, y, and this is our line we're rotating around, x equals 2. So our thickness is in the x direction, so we're going to be a dx. Our x values of our region, they go from 0 to 1. Keep in mind we're doing 2 pi RH, so I'll put the 2 pi out front. Our r is the distance from the line we're rotating around to our rectangle, so this black line that I am drawing in. That black line is not connected to an axis. So I'll add in this red line here. We know together the black plus the red should be always 2. And then we want to chop off the red part, so we're going to subtract something off. Well, the red part is connected to the y-axis, so that's an x. So our radius will just be 2 minus x. And we can put it right in as that because we have a dx. Now the height of your rectangle, notice our rectangle is attached to the x-axis, so the height of our rectangle is just y. Well, we can't put y in because it's dx, so we'll have to put in x minus x squared. We are now all set up to evaluate our integral. We're going from 0 to 1. We have to FOIL out. When we FOIL out, we'll get 2x minus 2x squared minus x squared plus x cubed dx. When we neaten that up, that'll be 2x minus 3x squared plus x cubed dx. And we're ready for our antiderivative. We'll have an x squared, meaning we need to multiply by a half out front, so 2 times a half is just 1. We'll have x cubed, so we need to multiply by 1/3 out front. Negative 3 times 1/3 is just negative 1. And then we'll have 1/3 x cubed. Wait a second. So that should have been I had a miswrite. That was x cubed. Let's rewrite this last one. That was an x cubed. So we should be an x to the 4th, meaning we need a 1/4 out front. And we're going to evaluate that from 0 to 1. So we'll have 2 pi, we'll have 1 squared minus 1 cubed plus 1/4 times 1 to the 4th, and 0 wipes out everything. So we'll have 2 pi, we'll have 1 minus 1 plus 1/4. So the 1's wipe each other out. We'll have 1/4 times 2 pi to just give us pi over 2. And that's the volume of our region, which we found using cylindrical shells. The 2 main new things is you draw your rectangle in so the long way is parallel to the line you're rotating around. And then the height of your rectangle should be bounded by your region, either on top and bottom or on left and right, depending how your rectangle was drawn. Here's a picture of that one that we just did. You can see we had our rectangle, we rotated around x equals 2, and one example cylindrical shell is drawn. That's all for today's video. We'll see you next class period.